This symphonic etude by Robert Schumann is full of explosive energy right from the get-go. Much of this energy comes from the fact that the melody and bass line move in opposite directions. As the melody leaps up to the highest registers of the piano, the bass line descends to the lowest registers. Later, as the melody is coming down from its heights, the bass line is rising gradually. Thus, the melody and bass line seem to be perpetually moving in opposite directions. Sometimes random variables can behave like this as well. Two random variables can tend to move in opposite directions. When the value of one random variable is small, the value of the other is large, and vice versa. We summarize the relationship between two random variables using a measure called the covariance. As you will learn in this video, two random variables that tend to move in opposite directions have a negative covariance. The covariance is a single number summary of the relationship between two random variables. The covariance between x and y is defined to be the expected value of x minus its mean times y minus its mean. This expected value can be calculated using 2D lotus. If x and y are discrete, then we sum over all possible x and y, the value of this function of x and y, weighted by the joint PMF. And if x and y are continuous, we integrate instead of summing, and we use the PDF instead of the PMF. Now, I think that this formula is the most intuitive way to understand covariance, as you will see in a minute, but it's not the most convenient for computations. You can check that this expected value simplifies to the expected value of the product of x and y minus the product of the expected values. This first term still has to be computed using 2D lotus, but x times y is a much simpler function than this function up above here. This second term only involves expected values of individual random variables, so this term is easy to calculate as well. Now that we've written down the definition of covariance, let's think about how we interpret the number that we get. Let's suppose that x and y can only take on one of 10 possible values, represented by these points here. Let's zoom in on a particular outcome like the one highlighted in red here. This outcome has an x value, which is above the mean for x, and a y value, which is above the mean for y. If we calculate x minus e of x times y minus e of y, both terms will be positive. A positive number times a positive number will be positive. So this outcome will contribute a positive value to this expected value. And in fact, every point in this upper right quadrant will contribute a positive value to the covariance. Now, there are also several points in the bottom left quadrant here. What will those contribute to the covariance? Let's look at the outcome highlighted in blue here. For this outcome, x is below the mean for x, and y is also below the mean for y. If we calculate x minus e of x times y minus e of y for this outcome, both terms will be negative. A negative times a negative is positive. So this outcome and all the outcomes in this bottom left quadrant will also contribute positive terms to this covariance. Of course, there are also outcomes that contribute negative values to the covariance, like the one highlighted in orange here. This point has an x value which is above the mean for x, but a y value which is below the mean for y. A positive times a negative is negative, so this outcome actually contributes a negative value to this covariance. But on the whole, when x is large, y will also be large, and when x is small, y also tends to be small. If two variables tend to move together like this, they will end up having a positive covariance, a covariance greater than 0. Now let's look at another possible relationship between x and y. Suppose x and y take on the 10 outcomes shown here. Now most of the points are in the top left and bottom right quadrants. For a point in this bottom right quadrant, x is above the mean, but y is below the mean, and a positive times a negative is negative, so these outcomes will contribute negative values to the covariance. Likewise, for a point in this top left quadrant, x is below the mean, but y is above, and a negative times a positive is again a negative, so these outcomes in this quadrant will also contribute negative values to the covariance. Of course, there are still some outcomes which contribute a positive value to the covariance, but on the whole, most outcomes contribute negative values to the covariance. So when x and y tend to move in opposite directions, the covariance will be negative. To summarize, the sign of the covariance indicates the direction of the relationship between the two random variables. A positive covariance indicates that x and y tend to move together in the same direction. Some people would say that they have a positive or direct relationship. A negative covariance indicates that x and y tend to move in opposite directions. Some people would say that they have a negative or inverse relationship. Now, we haven't talked much about the magnitude, but the magnitude of the covariance indicates the strength of that relationship. The larger the magnitude, the stronger the relationship. However, you have to be a bit careful when interpreting the magnitude of the covariance. Magnitudes aren't comparable across random variables. Just because x and y have a larger covariance than, say, u and v, doesn't necessarily mean that x and y have a stronger relationship.